think we should be live. So, good morning from Germany. um, okay, let's see. Let's wait a couple minutes. See if more people are joining. Just give some time to people as well. I mean, I guess if you guys can see me, if someone drops something in the chat, it's going to be super helpful. So I know that this is working, but it seems like it should be working. So basically, I don't know if all of you were in Sam's session yesterday, but the idea is we changed a bit the format and said, let's use the potential of each type of format the best we can. And so we said Sam is going to do sort of the more open discussion and sort of silent studying type of formula, whereas I'm going to be more like just hands-on, going through these my own way, my own style. And this comes with pros and cons, obviously, because this means you get the experience of someone reading the book or reading the text that hasn't really read it before, which I'm the kind of lazy type when it comes in terms of mathematics and stuff like that, so I might not be hi Ariel, nice to see that it's working. Hope not with a lot of delay, but yeah, so that's the idea, right? So I mean, I'm gonna be doing sort of my own style, and that might not fit everyone's way of approaching the whole thing, but I hope it gives insights to people on on how to use that. So I'm going to use, the good thing is I'm going to use the full 2 hours to just kind of go through stuff, and then if you have questions in the chat, you just ask them, and we can do sort of Q&A in general and all that stuff. So let's start right away, and let's not lose time with this. Feel free to try me at any time. I hope I'm still monitoring my network so I don't go offline again, but it would happen. If I go offline, I should catch it fairly quickly, so you shouldn't miss anything. So there's not going to be any open discussion in terms of blocking half an hour at the end or whatnot. It's just going to be all mixed time for the next 2 hours. So I hope that you all enjoy that. Good. So today, okay, so it's going to be a bit messy, right? I mean, I just 5 minutes ago I took a look at this stuff in here. It's like, ooh. So there's fun with matrices. There's a couple of things. My goal was to approach section 2. So there's going to be, and it seems pretty mathy. So there's proving universality. This can be interesting. Basic circuit identities. Let me just quickly take a look at these. So there's an introduction. Then we go through quantum gates, because I see there's some problems in there, and when I was talking to Sam the other day, I was like, I know there are some problems in section 2. Okay, so this is more like an introduction of the gates. And so I was thinking, I don't know where I read that. I don't know if this was while reading Mike and Ike, or while reading, because I'm sort of in the very beginning of the book, but I don't know where I read that. But someone mentioned, or maybe it was Craig from Algasert, I think he might have mentioned it. Why is it going so slow? Just want to go to the block. Where it's like it might pay off to sometimes when you've got the chapter of a book with problems, to actually approach the problems first without taking a look at the actual theory, just to double check. It serves two purposes. So to double check what your current what your current knowledge is, but it also helps to, when you go back to the actual theory, you're kind of a bit more engaged, I think, with or you're paying a bit more attention to certain details. It's like, oh yeah, that's going to help me solve that problem that I was not able to solve. So I'm quite tempted to do that right now. I know I said I would recap some of the stuff in chapter 1, but I'm almost like, screw that, and let's just go with these, and I'll probably go back and see if I'm missing bits and pieces to complete that, because it seems it's a good way to move forward, make sure I move forward with the book. Chapter 3, it's going to be challenging because it's going to be algorithms, and that's going to be quite heavy, but let's get down with this. So let's start with the problems. the whole thing is going a bit slow right now. Okay, so. And there's three sets of problems: classical logic gates with quantum circuits, basic synthesis of single qubit gates, building the best AND gate. Let's take a look at this. So, okay, so classical logic gates with quantum circuits. Using the NOT gate expressed as X in Qiskit, the C NOT gate expresses CX in Qiskit, and the Toffoli gate expresses CCX in Qiskit. Create functions to implement X, OR, and the NAND and the OR gates. Okay. No, I hope that's. Is this just an example? Yeah. Okay, let's give it a try. Let's see how. So there's the XOR gate. The AND gate. Why it's so slow? The NAND gate. Okay. The OR gate. Oh, and there's some tests. Okay. Okay, and they're all failing. Okay. Let's give it a try then. So let's just go ahead and copy that. I forget how to run things, you know, really easily. So now we've got another gate. So let's do an example. Let's take the example here, and then let's has this been copied or? Seems like. So this is basically defining a function. Let's go through the text. So I hope you can see that. I hope I'm not like blocking it with my camera. I might just move the webcam view to another place if not. Okay, so there's a qubit. Let's make that big for a moment so we can just focus on these. Quantum register, classical register, a quantum circuit. Okay, and then we encode 0 as the qubit state, 0 and 1 as the qubit state 1. Since the qubit is initially 0, we don't need to do anything for an input of 0. So for an input of 1, we do an X to rotate the 0 to 1. Okay, so this is just sort of an exercise to see. It's sort of a mixture of quantum and classical, I guess. Now that we've encoded the input, we can do a NOT. Wait a second. So that's just encoding the input. Okay, so it's just preparing the input. So if the input is 1, then you need to okay, and we're only allowed to use NOT, control NOT, and the CC NOT. Okay. Finally, we extract the 0 or 1 output of the qubit and encode it in the classical bit. So we do QC measure. Kind of realize after, like, we done the session a week ago, and I feel already rusty with the language. I'm not fully in shape. So get the backend, the Chasm simulator, one shot. Okay, and then return the output. And so if you do something like this, what was to was it shift enter? That works, yeah. And then if we go and copy paste the tests, something's wrong with the tests. Oh yeah, it's not wrong with the test, it's that those things are not defined. So let's just get rid of this for the moment. Okay, so input 0 gives output 1, input 1 gives output 0. That's what's expected for the NOT gate. Okay, so now we basically, I guess it's all about doing the rest. That doesn't seem it should be too complicated. Let's see. Maybe the limitation of the gates is going to make it complicated. Not. So the next is the XOR gate. So I see this is basically, okay, you're given the sort of the scaffolding of the whole thing, and then there's just how you modify at the very beginning. Your quantum program goes here. So Okay, so you measure, and then here goes the rest. But I guess we're gonna copy the input encoding part. I think that's something that must be there. So basically, you gotta encode that into your quantum circuit. So if input 1, and this is not gonna be efficient, folks. So don't criticize me for that. Input 1 is 1, then so we got two quantum resistors. Okay, so Q0 is so it's negated, and then basically if input 2 is 1, then Q1 is negated. So that should basically give me the right encoding. And so it's an XOR. So how are we going to do an XOR? So an XOR, it should be, let's see if the drawing tools work. Okay, so I downloaded this new thing here. I hope you can see that in the screen. But what the XOR should do, if this is input 1 and input 2, this should be, the output here should be 0, 1, 1, 0. So basically, I think that a control knot should be a knot. I think that's actually how even the control knot is sometimes explained, as in being the XOR, because the control knot. Okay, but I gotta output a 0, right? So, and I have only 2 registers, or can I add more registers? Because the thing here is, I guess nobody cares whether I add another register, sort of the outcome register, because the point here is I cannot, like, just operate with these two not register, sorry, one register with 3 qubits. So I think I can just do that. So I should do something like that, which is initialized to 0. And then basically, if I would say, if I control, so if I control on ones and say flip the actual output, maybe instead of talking I should be actually coding. So if I do something like so how would that be? QC control knot. Oops, it just went all gone. It's all gone. Okay. Anyway, control knot on the qubit 0 and the qubit 2, right? So basically, what this is going to give me is going to tell me, okay, so there's a if there's a 1 in the qubit 0, then my qubit down there is going to be flipped. Then I go and I do QC CX Q1 Q2. So what this is basically doing is if qubit 1 is 1, then qubit 2 is going to be flipped. Now the problem here is if both are 1, then this is basically going back to 0, the output, right? So this would be if this is the qubit, this is the circuit, then I do like this, and this is the control knot, and then I do another control knot in here. So this is gonna basically flip the whole thing back to 0, and so therefore I can't really distinguish between the output, like the input 0 0, but 0 0 or 1 1, right? I thought that would be trivial. So I might have to add some correction in here, right? Something to correct, or I can always add. I mean, at the end of the day, I can always add. That should be. So if now I say, yeah, it makes it difficult to just reason like this. Maybe with Quirk is gonna help me. So if I do like this, and I do like this, right? That gives me. So that gives me a. Feels it's easier like that. So that gives me a. For 0, 0, for 0, 0, I get a 0 back. For 0, 1, I get a 1 back, which is correct. For 1, 0, I get a 1, 1, 0, which is correct. For 1, 1, I get. Oh no, that's correct. Okay, I'm stupid. That should be it, right? I mean, let's give it a try. Clear. Should get rid of this. And so I should measure not Q1 but Q2. And I think that should be. So if I now go and copy the tests for the XOR gate, the tests for the XOR gate, yeah, okay, that's correct, right? Or should I check what the XOR table is now? That's correct. So the XOR is an exclusive OR, so it's, yeah, stupid. Okay, good. So the AND gate, good. That's an interesting one. I'm sadly I have to say that the thing here is as I'm doing another series in parallel, where I'm basically trying to decompose the TOEFL gate, which is an AND gate, and it's something that if I was not doing this right now, that would be a hell of a complicated thing to do. Because the problem with the AND gate is that okay, so let's see if I can. Oh yeah, wait a second. No, but it's not half complicated because I have a CCX, so I can use it. Okay, so that's cheating. The thing is that what's tricky is how to do that without a CCX. So literally, because the CCX is actually the AND gate, right? So if I just if I just go ahead and say okay, so I see here that there's probably a better way to do the XOR gate because you only have 2 registers in here, and I kind of cheated by changing that. I think you can, because my point is I'm assuming I don't want to destroy the but I don't care. I mean, I'm not destroying any inputs or anything, but I could just do this on sort of the same circuit, isn't it? Isn't just one control X actually an XOR? If I now, because now I realize this is a 2 in here, and I kind of modify it to 3. So if I stick to 2 and I say control X, so what's going to happen? So if it's 1 1, right? So if let's go back to the drawing here. So if I got 1 1, then this circuit is going to transform the circuit into 1 0. This is going to transform it into 1 1. This is going to transform the circuit into 0 1, and this is going to okay, that's easy. Sorry. I'm so stupid. It's like, what, it took me 10 minutes to realize that. Anyway, yeah, that should work. Because if you don't care and you say like I can reuse the, oh my god, that's just, I can reuse this part here, that should work. So this means basically that if I clear that and I say get done with this, and so that's it. Then you measure 1, and that should actually work as well. So let me check. Yep, that works. Simple. You see, sometimes you try to overcomplicate things, and here then it's kind of easy in the sense that I'll copy the same. I can almost actually copy almost the same and use the CC node. The CCX, and I think that should be like this, I think. And then you measure Q2, and then I go and copy the results for the AND gate, for the AND gate. Network is fine, everyone's fine, cool. Yeah, that's the AND gate. And now let's go for the NAND gate. Is the NAND gate, and that's a super basic question. It's, I guess, like an AND gate, but then negated. So it should be 1, 1, 1, and 0, correct? NAND gate table. That's cheating. Yeah, 1, 1, 1. So, I mean, I guess that this is as simple as basically negating the result. So if I go and do this, and then I say QC X on Q2, right? So I'm kind of negating the result. That should do it. That should do it. That should do it. That should do it. Yes, that's do it. And then the OR gate, and NAND and OR gate. Here I can use 3 registers. I guess the reason I can use 3 registers is because it's one of those operations that you can't really know the input from the input if you know the output, right? The same with the AND. This is something to do with reversibility as well, but we haven't touched that in the book, so I don't want to talk about it much. Oh, what have I done? No. Here. So, what would an OR look like? So, the OR is basically would give me 1 for all these cases, right? So, so I guess I can do sort of a, I mean, one way that I could do that is a sort of a reverse AND, in the sense that I say, first let me copy these. It probably doesn't look like I'm having fun, but I'm pretty stressed because this is so basic. Okay, so this here, and then, so what I would do is, I would negate both, right? And then try to run an AND, because then I should basically, with an OR, I should get a not an AND, sorry, an NAND. Exactly, because I should basically get the opposite of that. So I should get a 0 here, a 1 here, a 1 here, and a 1 here. And so if I negate that, that should work, right? So if why is it scrolling so badly? So if I basically copy that, so it's kind of copying that, but I gotta beforehand, I think, apply a next gate to 0 and 1, because I want them to behave the other way around. So I would do something like that, and like this, and like this, right? And then I think that should work. I think that should work. Let's test it out. Let's test it out. Here. I feel I'm bad at the keyboard today. Yes! Good. Okay, so that was pretty basic. Here you go. Basic, but it still cost me some trouble. It's good. Let's go to the next exercise. Let me check quickly the chat. Anything is all fine. Slack. Any comments? No. All good. So let's move on. Streaming seems to be working fine. So what's the next exercise? So we've done the first set. Let's take a look at the second set and the third set, and then let's see how this goes. So this is loading slow. Not good maths. Oh, okay. So we've got one exercise, another exercise. Interesting, and a third exercise. Let's go through. I don't know if I should basically save that and then save as, and I'll say set one, and then I'll create a new maybe notebook. That's probably the easiest way to start clean with this. So 1. Show that the Hadamard gate can be written in the following two forms. Ooh. Here the equivalence is used to denote that the equality is valid up to a global phase, and hence that the resulting gates are physically equivalent. Hint: it might be easiest to prove that that e to the power of I pi divided by 2m is equivalent to m for any matrix whose eigenvalues are plus minus 1, and that such matrices. Okay, so I don't think I can pull that off in terms of doing a sort of a mathematical proof. That's just not the way I roll. I can definitely take a look. Let's try to approach the problem at least. Let's try to kind of break down some of the things in here, and then see if when we go back to the chapter we can easily put the bits and pieces here. Now, it feels a bit odd if it depends on the audience of the book, right? It's really personal feedback here. This is the type of exercise that I would expect in a sort of a Mike and Ike type of book, but not like in a book that it's supposed to be really practical hands-on coding. But it's my personal taste, I guess. So show that the Hadamard gate. Okay, so what do I know? And here the problem is, okay, first I haven't read the second chapter, but I do have some background knowledge on this. So I know that the Hadamard is a rotation in between the x and the z axis of the block sphere. Now, what really helped me to see that is, which I've seen that in the session yesterday from Sam. There was sort of a feedback round, and someone showed Q control, and I want to show that again because that's the first time I think that I saw an animation of what the actual Hadamard gate is doing, and maybe it's somewhere else, but Q control. That's the block, but we can take a look at it, because for me it's before seeing that it was always like, oh, so it just goes from Z pointing up to the plus state. But you kind of don't realize the fact that for this rotation to work both ways, so that it goes from a minus state to 1 or a 1 to minus, this has to have a particular behavior, right? And products, pricing, industry solutions, resources. I don't remember how to get there. But I think it's in the gotta get started somehow. That's not what I want. Open controls, get started. Maybe that's something that's free. No. Maybe I'll just Google for Hadamard block sphere animation. That helped me a lot. Quantum Inspire. It can't be that difficult to find an animation of that. Velocity visualization. Oh yeah, I think that's a good. I mean, okay, it's not an animation, but that tells you. So it basically rotates like that. So it does this kind of like fancy thing around the sort of the edge, and then goes back here, and that means, so if this is X, right? How can I change the color of this here? So if this is Z and this is X, right? The basically the opposite should also work like kind of that. It's probably extremely confusing the way I'm painting it here, but it's like imagine the point in the middle is kind of centered, and then the rotation goes like that. So that's really I think that was really insightful, and I think that's somehow expressed mathematically with an x plus z. At least that's how in Quirk, for example, when you if you take a look at the yeah, so here you can see that it says it rotates 180 degrees around the x plus z axis. Now this kind of gives me an intuition that okay, there is definitely some relationship in here. So the Hadamard gate can be expressed in that form. Now I know that the square root of 2, this has to do with the amplitudes that you're going to then have at the end of like as a plus state or a minus state. So that kind of thing, it kind of makes sense. I don't feel like I would be able to formally prove that, or be a loss of time for all of you seeing me trying to do that. But that's definitely I think that makes sense. And then this part, I remember in the section 0. Let me go back to section 0. There was something in the linear algebra part that talked about exponentials. So exponentiating e to a matrix, which is pretty awkward, right? And it's all like, if I hadn't, there's a bunch of things that if I hadn't had the sort of the lack to have gone through, I would be totally lost in here right now. The one is this part in here, matrix exponentials, exactly. So the notion of the matrix exponential is a very specific idea, but one that is so important that it warrants its own section in this textbook. Because I remember we were doing that. So maybe there's something here that you could pull off to actually, or you could put together to use it to kind of make the proof. And so H is some Hermitian matrix. See, fairly straightforward, but wait, a matrix inside of an exponential seems super weird. How is this even still a matrix? Well, it actually becomes much more apparent when you expand our exponential function as a Taylor series. If you recall from calculus, the Taylor series is essentially a way to write any function as an infinite degree polynomial. If you go to find it, but the main idea is that you choose the terms. So okay. So, and if we choose fx equals e to the power of x, we can create an equivalent polynomial using the Maclaurin series, since the derivative of e to the power of x is simply e to the power of x. So I'm not entirely sure here of how I would interpret that, but I know also that if you take a look at, and it's funny because just go so slow, sorry for that. We were doing the problems. Why is this just scrolling so slow? It's probably just me, but so I'd recommend as well a video on 3 blue 1 brown, where they explain what's the meaning of e to a complex, to the Euler number e to a constant to the power of a complex number, which is like, if you think about it, just like how do you even interpret that, right? And it's really interesting to see that. So 3 blue 1 brown Euler, I think that's how you would basically find it the faster. Exactly. So I hope that the sound is not gonna just mute it. I want to skip the commercial, the IKEA commercial. Beautiful. So basically, the idea here is that what this means, it's basically rotations, right? If you plot sort of the function e to the power of z, z being a complex number, you'll kind of see that what it's doing is it's drawing a rotation. And so my intuition tells me that the reason you can do it this way is because it's because a matrix in this particular case can be interpreted as a rotation as well, right? So so it's almost like I would see the equivalence in there, but I'm not gonna be able to. And then the whole thing here is also it's pi divided by 2, so complex, so I times pi divided by 2. I don't know if this basically means I don't know if this basically means that you're rotating. It's like a Hadamard that rotates the other way around, right? Could that be? For example, if I were to make a gate here, and instead of the axis x plus z, I'd say 180 degrees. No, how could I do that? So trying to think about a way to put it in here, because basically the Hadamards, so Hadamard matrix is the Hadamard matrix is the following, right? That's not the, what's the Hadamard matrix? That's not it, is it? That should be maybe it's somewhere in quantum gates. Okay, so let's dive into this. So let's maybe see if there is here. Oh yeah, so that's basically it. Okay, so if I would add here I multiply that by I times pi divided by 2. I have the intuition this would basically give you a gate that rotates the other way around. This means instead of rotating, so if you've got the blocks, instead of rotating, instead of rotating counterclockwise, and this is like you got to imagine, you know, this being x plus z, that this is going to rotate like that. So effectively, it won't just change the result. So they are physically equivalent. That's my intuition here playing. And now this has stopped being responsive completely. At that point, I think it might be the plugin, the drawing plugin, that's messing up. There is valid as a demonstration on this expression on Stack Exchange. Oh, that's cool. I mean, I'm not gonna go in to take a look at those solutions if they already exist. I just wanted to see how my intuition would basically play in here, right? But if I would just say here, for example, I just wanna double check that. Let me do a quick reality check with myself. So the way I would write the matrix here would be basically 1 divided by the square root of 2. What should I use here? Exactly like that, like that, like that. And I think now I should do it negated, right? It's like a -1. Yeah, so that gives you, so this is counterclockwise, okay? So, but now if I would say I want to multiply that by pi divided by 2, then I should change that and say pi, no, so I times pi, and here I think that's how I should express it. And so that might be totally wrong, okay? I'm just trying to play with this idea. Okay, it's not. It's actually rotating in the same direction, but let's see. So let's call it the other Hadamard. But this seems to be, there seems to be the difference here. If I see this being the I think the stripes that represent the phases. So it seems there is like a global phase of 90 degrees that's applied to it. So, but if I would go ahead and now I have my gate in here and I will just apply it here, yeah, that gives me the same, you see? Okay, and if it's so I'll zoom in, and if I turn that into 1, it goes to minus, and if I duplicate this gate, it goes to 1, and this goes to 0. Yeah, so they are equivalent. But again, like I'm just playing with the exercise. I'm not going to really formally prove that because that's not how I roll, as I said. I'm not the type of audience. But basically, intuitively, I think that kind of makes sense. If I assume this is a way to represent the Hadamard gate, which I kind of feel like because of the what we've seen, not here, but in the other part of the Qiskit book, where it's like it's these matrix. Then if I just add that portion into it, it gives me the same type of behavior. So I'm assuming that's all correct and all that. Cool. So let's move on to exercise 2. And I'm sorry if I don't respond to the comments right away because I'm not. I have the chat sort of on the other screen, and I have to really still get used to it and look at the chat more often. So okay, exercise number 2. The Hadamard can be constructed from Rx and Rz operations. We haven't seen these operations yet, but I know these are rotations, right? So parametrized rotations. So again, if I didn't have the background knowledge, I would not be able to approach the exercise, I think. But it's just, I think it's fun to just go through the exercises before going through the actual chapter. And okay, so it can be constructed from Rx and Rz operations as well. So the Rx being a rotation on the x-axis and a rotation on the z-axis, which kind of intuitively makes sense to me, I think, because at the end it's a combined rotation, right? And so, see, I really want to find the Hadamard gate animation block sphere. I know it's maybe in here. No, that's the image. Yeah, but okay. Because it's just cool to see the animation, I think. But I guess my point, I'll try to draw it over here. Okay. So it's a combination of those things, right? So it's almost like if you would I'll choose another color. It's almost like if you would say, like, you could approximate that rotation by doing little steps like these and these and these and these and these, and I'm awful at drawing, but you get the gist of it, right? So it's kind of like you're almost rotating like first on the okay, no, that's not what that would be the y-axis. So you would rotate on the x-axis first. Let me clear that. So you would rotate on the x-axis first a little bit, then you would do a bit of a z rotation and like that, kind of whatever. It's like you can imagine. I think that's where this is going. It's sort of a stepping function. Like you're step by step, you're kind of approximating the smooth turn around the x plus z axis. Oh yeah, and I think that's what it means, really. It's a bummer that I cannot use this cross browser, but I guess that's what this thing here means. It basically says, okay, so rotate, so it's this whole thing applied n times, like this whole thing applied n times. And so this would probably mean apply a z rotation and then an x rotation of an angle that, okay, so and n approaches infinite, right? But if you just pick a really big number, so you're, let's say, I mean, maybe not a big number, let's say 10, right? So so you're going to repeat this 10 times in 10 steps. And so you want to split your angle, your final angle, which is basically 90 degrees, right, in 10 steps. And so you do 10 rotations on the z, 10x, like you do, but you do a tenth of the angle. I'm awful at explaining this stuff, that's why I don't teach. But I hope you get what I mean. So maybe let's see if we can animate or do something like that, to, because again, I don't want to prove anything here, but close. So what does it, okay, so what's the exercise about? First of all, for some suitable chosen is it theta? When implemented for a finite n, the resulting gate will be an approximation of the harmonic whose error decreases with n. Okay, so I guess the larger the n, the lower the error, because then you're approximating. I guess when you step the function, when you do like you approximate it, you might not end up exactly at the plus state, but close to it. The following shows an example of this incremental of this implemented with Qiskit with an incorrectly chosen value of theta, and with the global phase ignored. Determine the exercise is determine the correct value of theta. Show that the error when using the correct value of theta decreases quadratically with n. Okay. So what does this do? So theta is pi. It shouldn't be pi, it should be pi divided by 2, I think. Should it? Or not? It depends on n. So here they do n in 10 steps. Let me try one thing. How can I draw the, how is it, so Qiskit, draw the block sphere. I'm just having this idea where I would basically copy that. So let's execute that by hand. Just to again, I'm not gonna do the, I don't think I'm gonna prove that, but I just want to play with whether, to check whether my intuition is correct. So let's do that. Let's create a blank circuit, and then let's do this whole thing, but instead of a for loop, we'll just do this manually. Okay, so I'm gonna go with my guess and say that this should be actually pi divided by 2. And okay, so now what you're doing is I would be applying those 2 gates here, and basically what should I run? Can I just plot the block sphere somehow without having to run the whole thing? Otherwise, it's gonna bother me a lot, I think. Can I draw the block sphere? Let's see. Quantum circuit. That's not what I want to do. Visualizations, maybe that's gonna help me. What I want to do is I want to do step by step, and I want to basically draw the block sphere at each step and see where this little arrow is going. Interactive visualizations. Create a Q-sphere representation. No, that's not. Block multivector. Okay, a block sphere representation. So how does this work? Oh. So create a block sphere representation, graphical representation of the input array using as much block spheres as qubits are required. State vector or density matrix. So we can give it a state vector. Okay, so so that's how it, that's good. There's an so there's an example here. So you actually, okay, so I do need to measure and run it against a state vector simulator. Okay, let's try. But do I need to measure? Can I not just keep the measurement? I don't care about the measurement. Or no, I should measure it probably because getting the state vector is sort of something that's kind of illegal in a real quantum computer. Let's try without the measurement. So I'm gonna copy that paste. And basically, what am I doing? It's not. I guess that's not gonna work. So I get states, execute QC for this backend, and then plot that. Let's see what happens. Boom. Well, maybe I should import Qiskit first. Import Qiskit. No. How does this? Let's actually take the whole thing here and copy paste this thing. I didn't even have NumPy imported. But that's not plotting anything. Maybe I do have to measure. Let's see. Where am I here? Measure. What is this? What is this? What am I measuring here? 0101. If I do have to measure, let's take a look at this. What's that error? N is not defined. Why is N not defined? Of course it's not defined. Why it didn't break before though? Oh, because there's a loop in here. Okay, so you can see, because the code is then to plot how the error goes. Okay, sorry. So I'll just say, we'll just go ahead and say n equals 10. Okay, what else am I missing here? Index 4. So this is in measure. Do I really have to measure that? It's not defined. Really? Where do I need to import it from? From this one. Okay. Yeah, a lot of gluing, and I do need to Oh, it's worked. Okay, cool. Okay, but that's interactive, and okay, because nice. Okay, that's pretty cool. It takes a while to get there. Okay, but basically, so this is okay. So we've done a bit of a rotation in here. Okay, so. But how can it's probably impossible to turn that into an animation or whatever right now with the time we have. But okay, so it's kind of here, right? So do the effort and try to remember that. Oh, wait a second. What I'll do is I'll do it in the next cell. But without all this stuff. So just kind of copying everything again and running this. Stupid. I should run it. What I should do is, okay, now I'm running it 2 times. Okay? Exactly. That's what I wanted to do. Yes. So as you can see, it is indeed. So it's indeed starting to rotate, is it? Theta Q0. I'm not entirely sure. How could I? You know what I mean? I wanted to basically animate that, but it's not going to be. I could also try with Quirk. If this thing would just be not so laggy, I would be able to do a good job. So if now I do no. So I'm gonna take the whole thing again, but now I just wanna do like some step forward and do like these. And so I'm kind of rotating. Okay, and what's gonna happen now? If that works, sorry. Okay, so yeah, it seems it's working. You see now it's halfway the Hadamard. That's halfway the Hadamard. So by combining those two rotations, you're basically doing what I said intuitively. You're kind of doing, and you're eventually, if this is not gonna break now, eventually you're gonna end up somewhere close here. That's the idea. Okay, I think that's cool, honestly. At least validates my thought. You could also do it with, I think Quirk, the problem with Quirk is you're going to have a really small block sphere to take a look at these things. But if I was to parameterize, say, a... No, I'm not going to be able to do that here, because you can parameterize Z rotations. For a Z rotation, parameterize Z gate. Yeah. This one. You can parameterize this Z rotation and the X rotation, and then let that grow with time. Maybe that will work. Let's play with this for a second, because that could give me a built-in animation from scratch. So what is it doing? No. So I want to rotate. That's going to be difficult. I want this to rotate basically pi divided by 10 times, and then the t is what Quirk just uses to then add the animation part of it. So t times that. And here, same. So let's see, is this kind of working or no? Maybe I should tweak should actually have that. Because t grows from -1 to 1. Oh, that's not what... Okay, let's not get lost with these. Let's use the time more wisely. But you could eventually build, I think, a kind of an animation in here that does that. Okay, but that's the... okay, so it's almost 10. Good, we're halfway through, and we're, I think, almost done with the exercises. So that proves my point, I think. Okay, but I'm not going to approach the rest of the exercise as of right now. But I think it seems... so what the exercise is then doing is calculating the error. Okay, that's interesting. So the error is calculated based on then an actual proper execution of Hadamard gate. And then you see, and then you can plot that and see how it how the error kind of goes low. That could, I don't know, if I had the time I would just do that. Maybe, do we have the time? Let me see, let me think. Can we do that? So this whole thing here seems to work. Now step 2, run the circuit and see how many times we get to the outcome of 1. Because although I would just say go ahead and do it by yourself, yourselves, and because I also want to have some time to take a look at the actual theory. But it's definitely an interesting exercise to do. So you're comparing this error and then you're plotting the error. Yeah. I mean, actually, let's do one quick try. Let's be lazy and let's copy paste the whole thing and pick pi divided by 2 and not pi, if my mouse will react. So let's copy these. Let's go here and say we do this, but then instead of pi, we pick pi divided by 2, because that's the angle we're trying to the target angle we're trying to approximate, right? And now this is what's supposed to show me that it decreases quadratically with n probabilities and n. So I don't know how to visualize that correctly, but it seems like it's curvy, right? So it could be quadratic. Yeah, okay. So, but it's like with 10, you've got like a 0.1 error. No, wait a second, that's not correct. That's a really big error then, instead of 0.4. I don't get it. It's kind of increasing. Okay, it's something to come back to. Maybe I haven't picked the right angle, but that should be the right angle actually. So if I pick a big N, say 20, what's gonna happen? So it kind of stabilizes really quickly. But the error seems to be, is this the error, or is this the probabilities? I'm not really sure what I'm plotting here. Anyway, it's not really clear to me what I'm plotting here, but it's kind of curvy, so I guess that's good. He is decreasing, so maybe if I choose pi, because I'm convinced, quite convinced, should be pi divided by 2. But if I choose pi, what's happening? So now it's decreasing. Now the error is decreasing. So it's the wrong angle? Could be. Okay, let me take a look at the third problem. An improved, okay, it's an improved version of the approximation can be found. Okay, so what this is saying is if you, okay, so this is another way to approximate that with the okay, so it's a z rotation with theta divided by 2n, and then an x rotation, and then another z rotation. Interesting. Why would that be? Why would that be a better version? I mean, I guess that's just a better version. I don't know. Okay. Not perfect, but roughly perfect. But it's definitely a place and something to come back to. I'm not fully sure I grasp what's being plotted and how it's being plotted. It doesn't seem to fit my intuition in terms of the angle being pi divided by 2. Because that's the angle you're doing is 90 degrees, right? Pi is 180. So pi divided by 2 is 90 degrees. That's the final, it's kind of the final effect. What you're trying to approximate is that, basically. So that should be the thing. Okay. Maybe I'm just seeing this wrong. Anyway, let's go to the next exercise and see if we can maybe spend like 10-15 minutes on the last set, and then try to take a look at section 2. Actually, that's, I hope, why everyone else was here in the first place. So, building the best AND gate, and I suspect I know where this is going. So, let me save that as set 2. I'm gonna consider sharing those notebooks. They're really messy, as you can see, and without the context it makes no sense, but it's maybe useful for someone trying to go through these as well. Python 3. Good. So let's make sure that we import everything that's needed. In problem set 1, you made an AND gate with quantum gates. This time you'll do the same again, but for a real device. Using a real device, the real device gives you 2 major constraints to deal with. One is the connectivity, and the other one is the noise. The connectivity tells you what control X gates it is possible to perform directly. For example, the device IMBQ 5 Tenerife has 5 qubits numbered from 0 to 4, and it has the following connectivity. So not all the qubits can be connected to each other. I assume that's what it means. Here the 1 0 tells us what we can implement. Tells us that we can implement a control X gate between qubit 1 as control and qubit 0 as target. 2 0 tells us we can have qubit 2 and qubit 0 and so on. The noise of a device is the collective effects of all the things that shouldn't happen, but nevertheless do happen. Noise results in the output not always being the result we expect. I guess noise being basically errors, right? Things don't perform as they should perform. For the gates, noise levels can vary between different gates. The control X gates are typically more noisy than any single qubit gate. Okay. I'm assuming because it involves 2 qubits, the chances that something goes wrong are higher. We can also simulate noise using a noise model. We can set the noise model based on measurements of a noise for a real device. Valid try pi. Oh, now I see that. Let me try that. Let me see. How can I go back to? Can I go back to my notebooks in here? Can I just do that? Yes, set 2. So let's give it a try. Let's see what valid says. Pi. Let's go to the bottom. So pi. Oh, come on, valid! You removed it. Anyway, okay. Let's go back to what we're doing. Sorry. Thanks for trying to share that. Yeah, I guess you guys can go through these also at your own pace, and then share that. And for me, I just wanted to make sure my intuition was roughly correct. So I think we're in here. Yeah, probably because I haven't saved it. So okay, but that's basically this thing. I don't know if I am supposed to also probably create that coupling map in here right now. Probably. So you can also simulate noise with these, so that's a noise model. Okay, this is something that I'm really just copy pasting. Okay, errors type. Okay, so this is kind of defining maybe the error probabilities. Okay, that's interesting. Gate qubits. Interesting. Okay, so this is basically giving you a noise, a dictionary that then allows you to create a noise model. Okay. So you can done directly on on IBM-Q devices, but not to worry about all these. Okay, that's good. We'll create. I guess what they're going to do is create a a simulator that kind of behaves with this noise in mind and has that kind of limitations in here as well. I'll try that later. Sorry. Valid. I see now you're putting the correct message. I'll try that before we jump into the theory. Okay, let me just go through this first. So this is the this is the It's a nicer way to define the n. It's kind of the way that similar way that I did it. And now let's take a look and plot the results. This is from exercise 1, remember? So okay, so it's not perfect. It's like 89%. Wait a second. What is this? Probabilities? It's an and 0, 0. So it's almost always correct. It's 89% of the times correct, but then there's 10% of the times not correct. Still quite some error. We compare across all the results to find the most unreliable. Okay, so of all the possible inputs. So the input that's the most unreliable seems to be 0, 1. That's interesting, but not 1, 0. It's almost the same. No, sorry, that's the most reliable because this is the probability of a correct answer. So the most would be 1, 1. Funny. It's the one that should give you, that's the lowest. So the way this is done, I guess this is just comparing stuff in the code in here. So The AND function above uses a CCX gate to implement the AND, but you now know how to make your own. Okay, it's probably explained in the chapter. I have been playing with some of this stuff in some of my other series already, but it's so this is something that now we could just go ahead and try to implement an equivalent of the CCX gate. Find a way to implement an AND gate for which the lowest of the above probabilities is better than for a simple CCX. Okay, and that's it. So a couple of thoughts in here. It's basically that you just have to go and I guess figure out another way to implement a Toffoli gate without with minimizing those errors, right? The question here is it seems like it says control X gates have quite high errors, and so we should try to minimize the usage of those gates. And use as many one qubit gates as possible to implement the Toffoli gate. And I don't know if this is explained, but we can take a quick look at this. Basic circuit identities. I am suspecting this is going to go down this path in here. So I think it's going to be more about what type of one qubit gates. Oh, why does it look so messy? Have less errors. I smell this is the T gate. Why this is so messy? Is it just a rendering? Streaming is going well. Chat's going well. Okay. Control rotations. Okay, so there is indeed here a bit of a theory on how to implement a general recipe for implementing any controlled V operation, and then spoiler alert. Okay, so this is how you do it. Okay, good luck arriving to this by yourself. It's taking me. I didn't even get to that in my previous series, but I'm at a point where I almost got to. So I kind of had a strategy in terms of how you would do that, but with control X gates or control square root of X gates. But it's not. The point here is to use, I think, the T gates, because I think the T gate is the one that has the less amount of error. We're back to being able to quite a lot of gates. T gate. It is because. Okay, wait a second. It is because of this kind of application that gates are so prominent in quantum computing. In fact, the complexity of algorithms for fault-tolerant quantum computers is often quoted in terms of how many T gates they'll need. Okay, that's what I mean, right? So I think the T gates, for some reason, at least for the IBM fault-tolerant schemes, typically perform these rotations using multiple. Okay, Hadamard and T gates. I'll just try to refresh that, see if this rendering works well, because it's just messing up with everything. So, what is Valid saying? You can find a discussion about this angle on Slack Qiskit undergraduate. Scroll up and search for a discussion where there are 61 committees. Okay, cool. Thanks for the pointers. So, yeah, now it looks like it's rendered properly. Controlled rotations, the T gate somewhere in here. This is the qubits subject to noise, which basically consists of gates that are done by mistake. Simple things like temperature, stray magnetic fields, or activity on neighboring qubits can make things happen that we didn't intend. For large applications of quantum computers, it will be necessary to encode our qubits in a way that protects them from this noise. This is done by making gates much harder to do by mistake or to implement in a manner that is slightly wrong. This is unfortunate for the single qubit rotations Rx, Ry, and Rz. It is impossible to implement an angle theta with perfect accuracy such that you are sure that you're not accidentally implementing something like theta plus all this stuff. Yeah. Okay, there will always be a limit to the accuracy we can achieve, and it will always be larger than is tolerable when we account for the build-up of imperfections over large circuits. We will therefore not be able to implement these operations directly in fault-tolerant quantum computers, but will instead need to build them in a much more deliberate manner. Fault-tolerant schemes typically use the H and the T gates. The T gate is this, and it's a rotation around the z-axis by pi divided by 4, and so it's expressed mathematically as this. In the following, we measure that. In the following, we measure that the H and the T gates are effectively perfect. This can be engineered by we assume, by suitable methods for error correction and fault tolerance. Using the Hadamard methods is cast. Okay, so that's basically the reason why you use T gates to decompose it. I mean, I guess because look, I can show you what I had in mind. I'm not going to go through the exercise now because it's basically go ahead and implement that, and I guess you can implement that and then see that the errors, that the probability of correct answers is better in this case. And so, but my approach to build, my initial approach to build the Toffoli gate was more along the lines of using sort of partial, I would say, it's kind of like partially rotating and then correcting if you need to correct, right? So at the end of the day, what you wanna have is in your output qubit. Oh, come on. In your output qubit, you want to have an X gate applied when those two elements will be 1, right? So one way you can go about it is you can basically start rotating towards X. That will be the strategy, and then you kind of correct if needed. And so, you know, you would say, okay, so I've got a 1 in here, so I'm gonna rotate, right? But now if I have a 0 in here, I kind of want to correct that rotation. Sorry, not the X, but I'm gonna do a half X rotation, and that's why I didn't want to do that here, because I mean, if you're a beginner, that's and you're watching this and you're like, what the hell is going on here? This is another type of gate. I don't know if it's introduced in chapter 2 or not, but this is like you're doing an X but halfway. You're staying halfway between 0 and 1. So if there's a 1, rotate halfway. Now, if this still is a 1. But this is a 0, right? So if I do this, I'm now gonna basically, oh my god, I have to make sure. Why? I don't know if this is my internet connection or I have too many things open, but it's super slow. So I'm sorry for the bad experience here. So now if you've got like a 1 and a 0, right? Here you're gonna have a 1, so to say. So in this case, you gotta correct that rotation because you don't want that to happen, right? So you want to correct that rotation by applying the same gate that is rotating the other way around. But then you need to undo that. Yeah, exactly. But we're missing one thing, which is, you know, I mean, obviously, if this is a 1. Then we want to complete so now you basically have, okay, so if I see a 1 in here, I want to do half a rotation. If I see another one here, I want to complete the full rotation. But if I see that these, you know, either, because if this is 0 and so if it's 1 0 0 1, this part here is gonna undo that rotation. I think that kind of works. But basically, I mean, take a look at the other videos that I'm doing on these. Recently, they are in the Grover's algorithm for NISQ quantum computers, for NISQ computers and NISQ machines. That's kind of the general strategy, and I think the one with T's is really similar. But I think I should not now invest more time in diving into this, because I feel like it's not the purpose of the whole thing. I would love to usually get lost doing these things. That would be really. I don't know if here it's explained a bit, but it would be super helpful, I think. Is it explained? Let's take a look. So, by tracing through each value using these ideas we have already described, you could now implement each controlled V gate to arrive at some circuit for the doubly controlled U gate. It turns out that the minimum number of CNOT gates is 6. Okay, the TOEFL is not the unique way to implement an AND gate in quantum computing. We could also define other gates that have the same effect, but also introduce relative phases. Oh yeah, that's exactly what I'm doing now at that paper. If you go, I'll show you quickly. So you go to, if this is going to allow me to, of course. So if you go to Quantum Intuition YouTube, the YouTube channel, and you basically take a look at the videos, the playlist, sorry, and you go and take a look at the videos is going to be better. So home videos now. I think it's this one in here. I'm explaining basically that because I'm going through an example of that paper from Rod, where they basically come up with an algorithm for an implementation of Gerber's algorithm that works for NISQ computers that have exactly those limitations that the guide is explaining, right? Okay, I think I feel I'm going too off of a tangent right now with all this, so I'm just gonna go ahead and wrap it up with the exercises. And yeah, basically there is sort of a strategy behind this way of implementing, which is the same at the end, right? It's you're kind of step by step rotating towards your goal, and then you're undoing those rotations whenever you kind of catch the cases in the input that shouldn't actually apply the target operation. That's the idea. Okay. Any questions so far? I see still some people watching live. That's good. I think I haven't really gone offline. That's also good. And I'll just then basically take a look at section 2. Or maybe we'll skim through section 2 and then talk a little bit about section 1, and kind of try to wrap up in like half an hour or so a general view on chapter 1 and chapter 2 before we then move into the next sessions that will be deep diving into the actual quantum algorithms. This is why I really want to spend more time, because I think it's much more, it would help me much more to go through the book if you get your hands on actual algorithms even before all that. I know that some people prefer to go through the heavy maths first, but that's not the way that I like to do it. I like to kind of go back and forth, and then it helps me kind of understand a bit more how things work and why things are the way that they are. So let's take a look at the chapter 2. Let me just have a good sip. So and I'll make that maybe bigger for now, so you can read this better. I don't think you can read that better anyway, but yeah, maybe that's going to be easier. So then I can go back to the Jupyter notebooks if needed, because I think this chapter is not so much code intensive. Okay, but this is the introduction. So having some qubits is not enough. We need to manipulate them. Typically, the gates can be directly implemented in hardware. It will act only on 1 or 2 qubits. Introduction stuff. So the chapter then concludes by looking at small-scale uses of quantum gates. For example, how to build a. See, that's a bit. I haven't really read the last chapter of this, the last section of this chapter, but I didn't see there a sort of an in-depth explanation on why this works and why this is equivalent, which is maybe a bit like if I would be like I look at this circuit and I have no idea what's going on. Even having the background that I have to break it down mentally and kind of, okay, so that's what's happening, that's what's happening, that's what's happening. And even that part at the end, that part in here is still really obscure to me. I think that's the phase correction, because I think up until here you're doing the TOEFL gate, and then some nasty phase kickback is in there somewhere. You've got some phases that you want to correct, and I think that's what's doing this. But why you have swabs in here, I don't know. So this is not. If that would be explained, would make more sense, I think. But okay, quantum gates. So there's some Qiskit in here, but I think this type of Qiskit doesn't really. It's not really worth some latex stuff. Okay, so to manipulate an input, we need to apply the basic operations of quantum computing. These are known as quantum gates. Here we'll give an introduction to some of the most fundamental, I think streaming is going, yeah, fundamental quantum gates. So this means their actions understood in terms of the block sphere. Okay. The Pauli operators, the simplest quantum gates are the Paulis X, Y, and Z. Their action is to perform a half rotation of the block sphere around the X, Y, and Z axis. Therefore, they have effects similar to the classical knot. Specifically, the action of the X gate takes U from 0 to 1. The Z gate has a similar effect on the states plus and minus. I'm not so sure if I think the plus and minus state notation has been introduced before, somewhere in the prerequisites, I think. Okay, so this is how the gates are implemented in Qiskit. These are the matrix representations. It's like, I don't know, I think this type of content doesn't really, like, I'm not super tuned into this. It's definitely interesting, and it's definitely important to know some of this stuff when you want to maybe do some, reasoning yourself. I don't know. The job was to help us make calculations regarding measurements. Really? The matrix, okay. Their job, so much of these gates have already been shown in previous sections. Their job was, was to help us make calculations regarding measurements. But since these matrices are unitary and therefore define a reversible quantum operation, I don't believe this has. I think there's a comment in the discussion on yesterday's session about the same. It was like, I don't think this has been defined. What reversible is and why is this important. So we refer to the gates as X, Y, and Z gates. Hadamard and S. The Hadamard gate is the one that we've already used. It's a key component in performing a next measurement. This keeps bothering me a bit, like the concept of measuring the observable X and all this kind of stuff. It's so much not obvious until you really get into something like variation algorithms and simulation algorithms, where you're like, now I care about observables. Like if your problem doesn't care about observables, then I think that is a huge mental effort that you're putting into someone who's reading that, and it's like, why should I even want to measure the X? You know what I mean? It's personal taste, I guess. I was really confused, and if you take a look at my channel, you can see that probably for like 4 or 5 months I was like, why do you even need that? Like, I'm just always going to measure on the Z basis. And then when you get into simulation, then you understand why it makes sense, because then it's more than just X, Y, Z. It's about a particular thing you want to measure, right? And then this kind of has its own representation in there. But good. So like the Paulis, the Hadamard is also a half rotation of the block sphere. The difference is that it rotates around an axis located halfway between X and Z. This gives it the effect of rotating states that point along the Z-axis to those pointing along the X-axis and vice versa. So it turns 0 into, and let me stop here for a second. It's a personal critique again, but I think it's so important to understand the concept of interference that I almost feel like really confused that it hasn't been introduced up to that point now, because that's really at the core of almost everything you do in quantum computing, right? And let me explain what I mean. So let me just exactly. So if you've got like the 0 state, right, and the 1 state, and you apply a Hadamard gate. So let's say you apply a Hadamard gate here. Like, let's assume this is a given, right? So you're you have that, and in order to simplify notation, I'm just gonna write it this way. Okay, I know that I'm missing the the amplitudes and all this kind of stuff to make it like normalized and whatnot, but this is making it easy for me, and this gives you this way. That's basically what this section is telling us, right? So it's telling us here a Hadamard applied to a 0 state takes you to the plus state, which is basically that part in here. But it's not so obvious. For me, it would be super interesting if people would get insights in why does a Hadamard applied into the plus on the plus state takes you back to 0. This is where I think it's a neat way to explain. It's a clear way to explain what interference means for quantum computing, and it's like all the algorithms we'll take a look at later on. Most of them use interference at their core, right? So if you let me change the color now. So if you apply a Hadamard to these, right, you're basically, so I'll just go over here. That's slow. I'll have to change the tool, I guess. But that takes you to 0. Oh God, I don't even know where my mouse is now here. So 0 plus 1, that's your 0 here, and now if I want to unpack the 1, it's going to be 0 minus 1, following those initial definitions. So you can see that there's destructive interference in here, and we're only left with the zeros. And I think that's, if instead of just given that as an explanation, you explain here interference, I think that would open up a lot of eyes. For me, that was a big like, oh yeah, that's how it works. At least at that small scale. You can't. It's difficult to do that when you've got like more than 2 qubits, because then it's just too many, operations and stuff you do by hand in terms of canceling things. But it helps you illustrate that concept. It helped me. It might not help everyone, but that's. So I think that's an important thing that I'm kind of missing here. Maybe it's explained. I don't know, but. Essentially, it says the effect makes it an essential part of making X measurements, since the hardware behind quantum computing really only allows Z measurements. Again, that's confusing. Why would this be useful for someone who really doesn't know anything about simulations or quantum simulation, which is where the actual observables really become in handy? I guess probably people are like, shut up. There's many more cases where this is important, but without having those cases in mind, it's really abstract to understand why would this be helpful at all. So the property that Hadamard applied to 0 is plus also makes the Hadamard our primary means of generating superpositions. Yep. You've got the matrix form in here. So there are quarter turns of the Bloch sphere around the z-axis, and so can be regarded as the 2 possible square roots of the z-gate. Yeah, a lot of stuff in here that you need to carefully unpack if you're a new person to these. I agree that it would be helpful. It would be helpful to see sort of the rotations on an image. I don't know if making a sort of a GIF or like an animation would be cool or useful or not, but that's definitely important. What was SDG? Is SDG the S? It's the, okay, so it's the S dagger. That's why they were DG S dagger. Okay, so it's the inverse of the S. HS and S dagger gates along with the Pauli's. Other single qubit gates. We've already seen X, Y, and Z, which are rotations around the X, Y, and the Z axis by a specific angle. More generally, we can extend this concept to rotations by an arbitrary angle theta. This gives us the gates Rx, Ry, and Rz. the angle is expressed in radians, so the Pauli gate corresponds to theta pi. Their square roots require half of the angle, and so on. Yeah. So you've got two specific examples of RZ where they have their own names. So one thing that is still now I'm just seeing my video a bit in the preview delayed, and I see that my hand is covering my entire screen when I do when I use the touch screen. That's awful. I'm sorry for that you have to see my hand. Okay, but one thing that I'm still struggling with is the equivalence between RZ, like the RZ gate and the actual Z, T, and S gates. Maybe they are just special cases. Because I have the impression, because usually the Z, the S, and the T gates are cases where you can, so you see the relative phase is only applied to the one component, but if you think about an arbitrary Z rotation, like any other angle, that's also adding some kind of phase to the zero component. This still confuses me. It's confusing me. Forget that. It's not for now, not for today. But you've got basically these things in here. All single qubit operations are compiled down to gates U1, U2, U3. Before running on real IBM quantum hardware, for that reason, they are sometimes called the physical gates. Okay, so you've got a bunch of physical gates that you can compile all those into. U-gate. The IBM Q hardware, this gate is implemented as a frame change that takes 0 time. Okay. No idea what that means though. What is even a frame change? Multi-qubit gates. So to create quantum algorithms that beat their classical counterparts, we need more than isolated qubits. The most prominent multi-qubit gates are the 2-qubit CNOT and the 3-qubit Toffoli gate. These have already been introduced in the atoms of computation. They essentially perform reversible versions of the classical XOR and AND gates. Note that the CNOT is referred to as CX in Qiskit. We can also interpret the CNOT as performing an X. Oh yeah, there's been a whole so there's been a whole, I'll show you that. There's been an entire discussion between me and someone else in the Qiskit Slack. Michael Tracy, I think he's called. I hope you're fine if I show that. I mean, anyone can join these and see that because it's in general. But there's been a whole, like, there's been a bunch of discussions in here about the different interpretations of the control X operation, and I think it's worth you guys go read through that as well. It's an interesting discussion, and just basically my point here is that it's kind of interesting to see how like some people disregard the conditional interpretation of the control knot, saying that that it's just too classical and it's not, like, it doesn't help you think quantum, so to say. But I think it's useful in some cases. I mean, it's definitely useful when you're building things like the Toffoli gate to think this way. But it's maybe something that could be. So these together with, let's see if I can put my thoughts well structured in my head right now. So when I was starting to learn about quantum computing, I played the game Hello Quantum, right? And so this game is a game by James Woodon that walks you through the different gates and stuff like that. It's a really cool game. Well, that's actually my video. So what was really interesting is that the game basically gets to a point where they explain what the control Z gate is, and there are like these 3 ways to see to interpret a control Z gate at least. And so that was for me really shocking, right? That there's different interpretations, but at the end of the day, it makes a lot of sense. As the deeper you get into quantum computing, you realize that it's super important to understand that the same way you've got different dimensions within the block sphere you're measuring and moving things around, you also have different interpretations of gates, and sometimes some of them make it more intuitive and useful to understand an algorithm, and sometimes they make it just completely confusing. So the control knot is one of them, where it says basically you can think of it as a classical XOR. You can also think of it as performing an X on a target qubit, but only when the control qubit is 1. And I think there's another interpretation, which is basically as a phase swap. That's what Michael is explaining here. That you can see that gate totally as a phase swap. I'll explain you what I mean. So if you go to Quirk. And I apply, say I'm here, and I apply a T gate, right? And something like that, right? So pay attention that now you've got like a phase of 0 degrees here and a phase of, is this going to show up? Minus 135. Yeah. So if now I apply a control knot, damn it, this is so slow. I have too many things open. That's not working well. Apologies for these, but this is. I don't know if you see those things on your side, but I'm having big performance issues with my browser right now. If I apply a control X gate, you can see that the phases have been swapped. So that's another way to take a look at the whole thing, right? And it's really interesting. That you can just think of it this way as well, and so this definitely helps you in certain, in certain moments if you try to reason about why is the control knot being used in a particular algorithm, and maybe that's something worth putting into the book as well. That there's different interpretations for that. So with this interpretation in mind, we can simply define gates that work on the same way, but instead perform a Y or a Z on the target qubit. Yeah, that's another example, right? So there's so many different ways to see the control Z gate. The toughly, like a control Z gate can also be seen as, like, if I put as in a superposition of all zeros, and I apply a control Z gate, you will see that what happens, I don't know if you can see the effect, is this phase is, this particular element of your superposition, the one which is 1, 1, is phased by 180 degrees. That's another way to interpret that, right? So it's definitely worth. That's been the source of so much confusion on my side in my whole learning journey. That crazy. So composite gates. What is it? So when we combine gates, we make new gates. So if we want to see the matrix representation of these, we can use the unitary simulator of Qiskit. For example, I start something like, okay, an X gate and then a Z gate. Is that what it means? Or I know an X gate applied to one qubit and a Z to another. Okay, so and then you're combining that gate into these. Okay, and then you kind of make the matrix out of that, so you could use that as a single block in your algorithm. So you're doing here, what are you doing? You're doing the unitary simulator, and then what are you getting? Get unitary, and then you use the fanciness, some fanciness to display this in LaTeX. Okay, so basically the get unitary gives you the matrix to represent that. Okay, interesting. I feel this is quite heavy. I feel this is quite heavy for just like 2.2. But let's go ahead, fun with matrices. I want to spend the next 15 minutes kind of trying to go through. I already know that I'm not going to go through 2.5 proving universality. It's not how I roll. I think it's a fun thing to go through. Probably it's just interesting mathematically, but I don't see the usability of these for someone who just wants to get into, get as quickly as possible into understanding what's the different mental model or computational model for quantum computing. So fun with matrices, manipulating matrices is the heart of how you analyze quantum programs. I would disagree with that. Okay, I mean, yeah, if you want to analyze it mathematically, then yes. In this section, we'll look at some of the most common tools that can be used for these. Unitary and Hermitian matrices. Studying universality is inherently an endeavor that needs math. You see, that's where it's like I don't have anything personally against these kind of statements, but if I would just go that, this would just turn me off. I mean, I'm not like, okay, sorry. Let me, no. Let me correct that. I'm gonna correct myself. If you want to study universality, then yes, that needs math. Correct, but not quantum computing in general. So first we need the concept of Hermitian conjugate. Yeah, I feel like this is math. Matrices as an outer product. Spectral form. Pauli decomposition. What is a Pauli decomposition? So I guess a lot of the tools presented in here will probably help. Okay, I kind of see here. I think this is probably going to help you get that exercise with the demonstration of the Hadamard gate and whatnot. Yeah. It seems like this. But like, I'm not. That's not. This is not me being lazy. I mean, it is me being lazy, but this is not me being. Yeah, I don't care about maths. That's how I would actually approach it. So, I'm not. I would tend to just come back to these things later on if I really think that I need them. C. The standard gate set. So, Clifford gates. The standard gate set. For every possible realization of fault-run quantum computing, there is a set of quantum operations that are most straightforward to realize. Often this consists of multiple so-called Clifford gates, combined with a few single qubit gates that do not belong to the Clifford group. This section will introduce these concepts in preparation for showing that they are universal. Okay, so I guess I'm gonna skip that. I'm sorry. It's just I don't like doing these things. I get it. I should, but I'm not. And math is fun. I mean, don't get me wrong. Math is fun. Like, it just, I don't know. I don't feel like it. But there's some interesting identities in here. So if you do a Hadamard, an X gate, and a Hadamard, then that's a Z gate. But I think it would be much more helpful to see those things, I don't know, graphically with a block sphere, playing with code. So there's some identities in here that, okay, I think again, the purpose of introducing all that is to then have the right toolset to prove universality, which is totally. But if I was to suggest a change in the chapter structure, like this whole thing here for me would go to the very end of the book as a that's an annex you want to take a look at if you want to dive into the maths behind universality and all this kind of stuff. So a book that does a great job for people that are for an audience that is a bit more like me is the O'Reilly book, like. Because they basically go ahead and let's see if I can Kindle, if I just can go to just show the chapter structure. So quantum computing, the table of contents. And again, that might be the wrong. I might be the wrong type of audience for the Qiskit textbook, but that's. I mean, I'm being honest here, so that's my take on this. So there's an introduction to the whole thing, and then there's basically notation, a bit of the basic instructions, and then you start talking about multiple qubits. What I liked is that you jump right into. Oh, come on, go to. This doesn't work. I guess it's collapsing. So again, here. So then you jump into amplitude amplification. I don't remember quantum phase estimation. It gets practical really quick, and I also like the fact that you start right away with arithmetic, And what I really liked is that instead of this is also to give input to the people that were in the previous session, where the people say, it doesn't, the half other example of the first chapter doesn't really help you understand the power of quantum computing. The way that this book approaches it is like they show you the arithmetic, and then they say, you know what, you can do arithmetic with and within in encoding the results in the phase, right? So it gives you that kind of, that's when it gives you I was like, oh, there's more to that than classical computing. And so that's something that I really personally liked. But again, this is just my my 5 cents. And if this thing would just work for once. Yes. Okay, so this is all composite gates, proving universality. So this is awfully slow, and I don't know how to make that better next time. So I'll have to work on this in terms of the how the browser is performing. It just, there's such a big lag. Maybe I should close some of these things. I don't know. Close these. So proving universality is 2.5, which is not opening. So how much more time we have? 10 minutes, kind of 10 minutes. Okay, now it's going better. Proving universality. So yeah, I guess not doing that. But what is it? What's the gist of it? So with a few Hadamard's, I mean, I guess intuitively you can think of, if you think about a block sphere and you're just like, okay, with a Hadamard, not with Hadamard, like with rotations, you can just go everywhere, right? If you have the rotations across, like, I think even just 2 of the angles, right? Like 2 of the axes, you would potentially be able to reach everywhere. I think that's what I would intuitively think about. Yeah, Rx and Rz, I think. Okay. But I guess with a Hadamard, with a T-gate and a Hadamard, you could, I don't know. It's, yeah, that's, I personally think that's just for, and again, it depends on the audience. If your audience is someone who's using that as that material as supplement for like a university introduction into quantum computing and quantum mechanics, I think that's definitely not bad. But I'm definitely not that type of person. But basic circuit identities, making a control Z from a control NOT. You see, the thing is, I'd focus less on the actual technicalities of how you build those gates using other gates, but more about the interpretation of them. I think that's something that if I had gone through that before in a more consistent way, I would have had an easier time understanding certain algorithms. So there's swapping qubits. You can do that with control X gates. Don't you need though 3 of them? A, B. Oh yeah, BA, AB, BA. Some A1, A1 from A to B, but with a useless at the beginning. We can also think of it as the process that swaps a 1 from B to A, but with a useless BA at the end. Either way, the result is a process that can do the swap both ways around. Yeah. Here I'm missing a beat. Was there an introduction to the no cloning theorem and stuff like that? I know this is more quantum mechanical and maybe feels like less practical, but it's also interesting to understand why why the swap has to be done this way. So making the C-nots we need from the C-nots we have. These gates in the quantum computer are driven by the physics of the underlying system. Changing the direction of a C0. Let's do with the second problem described above. If we have a C0 with control bits qubit C and target qubit T, how can we make one for which T acts as the control and C as the target? This question would be very simple to answer from the control Z. For the control Z, for this gate, it doesn't matter which way around. You see, and that's then you drop in those sentences without having gone through the different interpretations of the control Z, and it's pretty confusing, I think. So, you know, control Z CT is the same as control Z TC. For a control Z gate, the control qubit must be in state 1 for Z to be applied to the target qubit. Given the above property of Z, this only has an effect when the target is in the state 1. This is even more confusing. We can therefore think of the control Z gate as one that multiplies the state of 2 qubits by -1. But only when the state is 1, 1. Yeah, that's quantum fun. Okay, so this is a way you can reverse the controller and the X gates, I'd guess. Here's another way to write the C0 gate. Why would this be useful for? I guess it's useful for some other reasoning in there, but it's pretty heavy, all this stuff. Like I'm like out of laziness just scrolling through that. Not because I have done this before, but because I think I've been facing some of this material before in other forms and shapes, but just doesn't appeal enough to me. Controlled rotations. So that can be maybe an interesting thing. So how do you build controlled rotations? Or how to build any kind of controlled gate, right? That's common. That's a question you would think of. It's like how would I do that? I mean, obviously, with an editor like Quirk, you can drop the control thing anywhere, and you can even do like a control Hadamard. But like how you would build that in Qiskit, right? Because you don't have a CH operation, I guess. So, and I guess the gist of this is, I don't know how this is explained in here. This method works because x and y axes are orthogonal, which causes the x gates to flip the direction of the rotation. Therefore, similarly works to make a control RZ, a control RX could be similarly used to C0 gates. We can also make a control version of any single qubit rotation. For this, we simply need to find 3 operations A, B, and C, and a phase alpha such that, yeah. Yeah. I guess the strategy here is here A, B, and C are gates that implement A, B, and C. Okay, but the strategy is kind of this. It's kind of the same as in like you're. I don't want to open the drawing tools because it's going to break the whole thing again. So you're basically approaching your your V gate effect by using. Okay, control Zs. Control Zs, or is this just a Z? As in like, yeah, I think it's a control Z. So you're kind of doing and undoing based on this, and then I think this little guy up here is just a phase correction. That's what it is. And then the Toffoli gate is the 3 qubit gate with 2 controls and 1 target. It performs an X on the target only if both controls are in the state 1. The final state of the target is then equal to either the AND or the NAND of the 2 controls, depending on whether the initial state of the target was 0 or 1. A Toffoli can also be thought of as a control NOT, and is also called CCX gate. To see how to build it from single and 2 qubit gates, it is helpful to first show how to build something even more general, an arbitrary controlled U for any single qubit rotation U. For this, we need to define controlled versions of. Yeah, so that's the strategy, right? So you're approaching. Okay, so V would be, so if your target is an abstract gate U, you want to define gates that are sort of getting halfway that. That's what the square root of U means, really. You know, kind of go halfway that operation. And then V dagger is kind of go halfway backwards. So you're undoing the path you've already gone through. So By tracing through the value to control bits, you can convince yourself that a U-gate is applied to the target qubit, even only if both controls are 1. Using ideas we have already described, you could now implement each controlled V-gate to arrive at some circuit for the doubly controlled U-gate. It turns out that the minimum number of CNOT gates is blah blah blah, and then this is being dropped in here, which is a monster of a complication to try to understand that. But it's not. This is not the guide's fault, I guess. It's just I don't know. What's my take on all these? Just to close it up, wrap it up for today. It's 11. I could spend like 2 or 3 more hours on these, and I really haven't even gone back to chapter 1. I'm sorry for that, but it's my take on this. I'm happy that I went through the problems first. I think that actually definitely helped me to get my hands on dirty with some of the stuff, and I felt a bit that the problems were a bit disconnected from the actual like mathy stuff. I mean, if you really want to go and make the proof of this problem here, then the mathy stuff is definitely helpful. But you can see, if you go through the 2.3 fun with matrices, this probably gives you the right tool set to approach that demonstration, like that demonstration. I think that that proof. I don't know. I'm probably using the wrong English words. Yeah, so that's probably it. I mean, I'm happy that I went through the exercises. That's my take on these. I personally think that for a certain type of audience, that's not the optimal 2 first chapters or 3 first chapters. 0, 1, and 2 feel like super heavy on math, which is not a complicated type of math, but it's just heavy on math. And you know, people not doing research as their full-time type of job might just have some hard time getting used to it. Now, whether this helps you to approach the algorithms in chapter 3 or not, that's an interesting question. We'll see, I guess. I'm gonna structure the next sessions just focusing on the algorithms, you know, 1 or 2 at a time. Try to understand how this is explained in here, and then try to break them down somehow, so you see what's the mental process that I usually follow to approach those things. But it's all in all feels a bit like it's difficult to give concrete feedback. You know, it's kind of cool. You was clear. Okay, thank you. Thanks, Valid, for the nice feedback. I mean, it's difficult to just, you know, put all the mental process through my mouth, like going from my head through my mouth, so that you get what is going on in here. And don't get me wrong, I'm not saying the way this content is built in here is wrong. I mean, it seems to be everything, you know, of course, correct and whatnot. It's just doesn't feel things are in the right place. That's maybe my feedback, but definitely approaching the problems first was a good thing. So I don't know, is there any other questions? If not, you know, happy to you know, answer comments later on if you put them on the video once it will be available on the channel. And, you know, see you next week. I mean, I'm enjoying this a lot. It's actually quite tough to squeeze all this stuff in one in like 2 hours. But it gives you an idea of how at least I would approach reading the guide and reading the book, and that it's not always easy, because you can't avoid going back and forth. Let's be honest, you can't avoid going back and forth. So it's something you have to live with, and, you know, it took me 15 minutes to figure out how to do an XOR gate when it's just a control X gate. So no shame in here, I guess. Thanks for the people who've been joining and, you know, through the whole thing. Hope you enjoy the content, and, you know, feedback in Twitter, feedback in Slack, in the Qiskit Slack, feedback on the channel. Everything is welcome. And there's another session later today that is going to give people more time to work on those things by yourself, and then ask more in-depth questions that you can ask via the channel, via the chat in here. So hope you guys have a good rest of the day, and we see each other next week on Sunday. Cool. Thank you, and bye-bye.